Thank you very much for the introduction. And I'd like to thank the organizers for organizing this conference in this difficult situation. Thank you very much. And I'm Shinichiroh Matsuo from Nagoya University in Japan. I'm talking about the Atiyah-Patodi-Singer index and domain wall fermion Dirac operators. And this talk is based on this paper. You can find it on arXiv and which will appear in Communications in Mathematical Physics. And this paper is a collaboration of 3 mathematicians, Furuta, Yamashita, and me is a mathematicians. And 3 physicists. Fukaya, Onogi, Yamaguchi are physicists. And these 3 physicists are conjectured and proved physically by a physics method some formula about the Atiyah-Patodi-Singer index and in some special cases. And we mathematicians together with us, we 6 proved it mathematically rigorously and in complete generality. Let me start with a brief summary of my talk. This is a main theorem. For m very, very large, we have a formula which relates the Atiyah-Patodi-Singer index in terms of the Eta invariant of domain wall fermion Dirac operators. This blue one is a domain wall fermion Dirac operators, which I will explain later, and I will define it mathematically rigorously. So the main theorem relates the expresses the main theorem in our main theorem. The Atiyah-Patodi-Singer index is expressed in terms of the Eta invariant of domain wall fermion Dirac operators. And the original motivation comes from physics, especially bulk edge correspondence of topological insulators in condensed matter physics. And our proof is based on a Witten localization argument. This is the plan of the talk. Let me first review the usual Atiyah-Singer index theorem index on closed manifold, and let me review the definition of the Eta invariant. And then next, we move on to the case of compact manifold with boundary. So that is, we will review the definition of the Atiyah-Patodi-Singer index. And then next, we move on to one of our main topics, domain wall fermion Dirac operators. And then next, we restate our main theorem rigorously, and then go on to the proof. First, I will prove some toy model, a very, very basic formula in the spirit of our main theorem. And then next, we move on to the proof of our main theorem. This is a plan, okay? Now, let me start with the brief review of the Atiyah-Singer index and Eta invariant. Let me set up some notation. Let X be a closed manifold, and S is a Hermitian bundle on it. We assume throughout this talk, we assume dimension of X is of even dimensional. And we also assume that S is Z2 graded in the sense that there exists a morphism of gamma from gamma S to gamma S such that its square is identity. So gamma is of this form. And let D be a first order elliptic differential operator on S. And assume D is odd and self-adjoint. D is odd if it anti-commute with gamma. So D gamma plus gamma D is equal to 0. So if D is odd, D is of this form. And we also assume that D is self-adjoint in the sense that D is equal to its adjoint. So combined with this form and this condition, we get D minus is equal to D plus star. And we now define index of D to be the dimension of kernel D plus minus dimension of kernel D minus, which is equal to dimension of kernel D plus minus dimension of co-kernel D plus using this one, this equality. Okay, this is the usual Atiyah-Singer index of D, odd self-adjoint of eta D. Next, we want to define Eta Invariant in some particular case. Fix some real n, which is not equal to 0. And consider this operator, D plus M gamma. And this is of this form. This is self-adjoint because this is self-adjoint, but no longer odd because of this diagonal term. So its spectrum is real because it is self-adjoint, but it's not symmetric around 0 because it is not odd. So we want to describe its overall asymmetry of its spectrum. This is Eta Invariant. In order to define Eta Invariant, we first define eta function of D plus M gamma. Let Z be a complex number with its real part is very, very large. And we define eta function of D plus M gamma to be this one. Here, lambda J is a spectrum of D plus M gamma. And as I assumed M is not equal to 0, lambda J is not 0 for any J. So this, and for Z with real part very, very large, this function converges. And Atiyah and Patodi and Singer proved that we can extend this function, eta function, meromorphically to the whole complex plane. And moreover, they proved that 0 is not a pole. So we can define eta function, eta invariant of D plus M gamma to be the 0 of this eta function, eta D plus M gamma 0. This is eta invariant. So it describes overall asymmetry of its spectrum. Okay. Now there is a formula which relates the Atiyah-Singer index and eta invariant of D plus M gamma. So for any M positive, we have a formula. Index of D is equal to eta invariant of D plus M gamma minus eta invariant of D minus M gamma divided by 2. Perhaps this formula might be unfamiliar to you, but we can prove it easily. For example, D and gamma anti-commute, but D squared and gamma commute. So we can diagonalize them simultaneously, and using this fact, you can prove this formula easily. But anyway, this is a toy model, as I said in the plan of my talk. So I will prove this formula in the spirit of our main theorem. And what we want to do is to generalize this formula to handle compact manifolds with boundary. So in order to deal with compact manifold with boundary, we need to introduce the Atiyah-Patodi-Singer index. oh, this is our main theorem, and this is what we want to do here. In order to generalize to the case of compact manifold with boundary, we need to introduce domain wall fermion Dirac operators. Next, we briefly review the definition of the Atiyah-Patodi-Singer index. So far, any question? Is X oriented? Yeah. We don't need an orientation assumption.
Sorry, I have a question. In your definition of Eta invariant, it seems like the right-hand side doesn't depend on Z.
Pardon?
Yeah. I mean, so the right-hand side, where the right-hand side depends on Z.
Z is here.
So the exponential, yeah, okay.
Are there any questions? Does this definition depend on K? Which definition? Now let's move on to the compact manifold with boundary. Page 7. Does this definition? You mean definition of domain wall fermion Dirac operator? Anyway, the question is
the right hand.
What is K? I will explain what is K later.
Okay.
So I will explain in detail what is domain wall fermion Dirac operator. Now let's move on to the Atiyah-Patodi-Singer index. So we further assume that this is X. This is X and closed and even dimensional. And we further assume that there exists Y, which is a separating submanifold, which decomposes X into two compact submanifolds, X plus and X minus, with common boundary Y. And assume Y has a standard tubular neighborhood isometric to this finite cylinder. So here, Y has a standard neighborhood. This is our assumption, a standard setting. And we also assume S bound on X and an operator on it are standard on this finite neck. In the sense that there exists a Hermitian bundle E on Y and a self-adjoint elliptic operator A on E, such that S is E plus E, C2 times E, and D is of this form here. So in this sense, D is translationally invariant on this shaded region. Okay, this is also for simplicity today, we will assume that A has no zero eigenvalues. So A is invertible. Now we want to define Atiyah-Patodi-Singer index in this way. Let X plus hat be this manifold. X is separated by Y, and this is X plus and X minus, and remove X minus. And glue this semi-infinite cylinder to X plus, and we get X plus hat. This is a cylindrical end manifold, And as we assumed D is translationally invariant on this region, so thus D restricted to X plus can naturally extend to X plus hat. And we will denote it by D hat. And since we assumed A has no zero eigenvalues, this operator D hat is Fredholm. And we define Atiyah-Patodi-Singer index of D restricted to X plus is equal to index of D hat. This is a definition of the Atiyah-Patodi-Singer index. Okay. Now let's move on to the domain wall fermion Dirac operators. This is a very simple object. Let kappa be a function on X, which is discontinuous, step function, discontinuous. Such that kappa is equal to +1 on X plus, and it is equal to -1 on this region. And kappa is this function, and we define for any m positive, this function d plus m kappa gamma. We call this d plus m kappa gamma is we call this d plus m kappa gamma a domain wall fermion Dirac operator, because that gamma is a D2 grading operator. Gamma is +1, -1 from gamma S, section S to section S, and its square is identity. So D2 grading. This gives a D2 grading on S. So kappa is called a domain wall function. And this Y is called domain wall. And domain wall function has a singularity discontinuity on Y, domain wall. This is a definition of domain wall fermion Dirac operator. Very simple object. Now, D plus m gamma, D is of this form. D is odd and self-adjoint. And gamma is of this form. So D plus m kappa gamma is of this form. So this is self-adjoint, but not odd because of this diagonal term. And we have a proposition that says, as I assumed A is invertible, A is this operator, D is standard on this region. And D is translation invariant, and A is a operator on Y. And I assumed A is invertible. In this situation, if A is invertible, then for any m very, very big, D plus m kappa gamma domain wall fermion Dirac operator is also invertible. So we have a self-adjoint, not odd, invertible operator. So we want to define the Eta invariant of domain wall fermion Dirac operator, but domain wall fermion Dirac operator has a discontinuity. So we have some care. Now, we want to define the Eta invariant of domain wall fermion Dirac operators, which is discontinuous. Since, as I said to you, D plus m kappa gamma is invertible, and the invertibility is an open condition. So there exists a constant C such that a slight perturbation of deep domain wall fermion Dirac operator is also invertible. And based on this fact and the variational formula of the Eta invariant, we can prove that assume the perturbation of m kappa gamma plus F1 and m kappa gamma plus F2 are smooth. And this perturbation is very, very small in the sense that F1, L2 normal F1 and F2, L2 normal F2 is very small. This Cm is this constant. Then, because D plus m kappa gamma plus F1 is smooth, and this one is also smooth, as I assumed, we can define their Eta invariant, and they are equal by the variational formula of the Eta invariant. And using this corollary, we can define the Eta invariant of domain wall fermion Dirac operators, which is discontinuous. So for any F with slight perturbation, such that m kappa gamma is smooth, we set Eta invariant of domain wall fermion Dirac operator to be this one. This is well defined because of this corollary. Okay. Now we have first reviewed the Atiyah-Singer index and what is I have reviewed Eta invariant, and we introduced Atiyah-Patodi-Singer index, and then we defined the domain wall fermion Dirac operators, and it's in Eta invariant. Now we can understand our main theorem mathematically rigorously. So this is our main theorem. There is a question. Why introduce F? Because kappa is discontinuous. Now, are there any questions? Now let's move on to our main theorem. This is our main theorem. For m very, very big, we have a formula. In the Atiyah-Patodi-Singer index of D restricted to X plus can be expressed in terms of domain wall fermion Dirac operator, Eta invariant of domain wall fermion Dirac operators. And in physics, this is called Pauli-Villars regularization. But if you do not know this word, you can just ignore it. Anyway, this is our main theorem. The Atiyah-Patodi-Singer index is expressed in terms of the Eta invariant of domain wall fermion Dirac operators. And the original motivation comes from physics, especially bulk edge correspondence of topological insulators in condensed matter physics, especially Witten's paper on topological matter. And also the motivation comes from lattice gauge theory. And our proof is based on a Witten localization argument. And we move on to the proof. And as a warm-up, we want to prove a toy model. What is toy model? This is a toy model. The proposition I mentioned before. For any n, why not? You mean this one? Why not?
Yes.
Yeah, this is a point. So just a moment, I will come back to it later. not symmetric. There is, so, but good question. There are no gamma, no kappa. No kappa. This formula is symmetric. But our formula is not symmetric. Thank you. Are there any questions? Then let's move on to the toy model. Toy model says that for any m positive, we have a formula. Index of D is equal to eta invariant of D plus m gamma minus eta invariant of D minus m gamma divided by 2. As I said to you, you can prove it easily by diagonalizing D squared and gamma simultaneously, but we will give you another proof based on our idea. Idea is embed everything into a cylinder. This is a cylinder. This is our direction, and this is x direction. We consider r times x. And we want to introduce kappa hat AS. AS stands for Atiyah-Singer. And let kappa hat AX is a function on r times x, this cylinder. And this is also a step function, discontinuous function. Such that kappa hat AS is equal to 1 in this region. This is infinity times x. And kappa hat AS is minus 1 in this region. So kappa hat AS has this form. And we consider this operator, D hat M. This is an operator on this cylinder. And this D hat M defined by this. This is D plus M kappa hat S gamma minus dt. T is this, the coordinate on our direction. So because D plus M kappa AS and because M is not 0, M is positive, not 0, this operator D hat M is Fredholm. So this is a model case. Domain wall fermion Dirac operator on R. This is in physics literature, this is called Jackie-Levy solution on R. For any n positive, we have this distributional equality. Differential of e to the minus m, the absolute value of t, is equal to minus m times sine function times exponential to e to the minus mt. Here sine sgn plus minus t is a sine function, this one. So ddt plus m sine times e to the minus mt is equal to 0. And this is a domain wall function. And this, the origin is domain wall. as you can see, if m gets bigger and bigger, then this function is concentrating at the origin. Okay. So this is a one-dimensional domain wall fermion Dirac operator on R, and this is a typical solution, which concentrates at the origin as m grows. Okay. We will use this solution later. Now, we can prove this product formula using this Jackie-Levy solution. Solution. Recall that kappa hat AS is this step function on x times r times x, and d hat m is this operator. And as I said to you, this is the Jackie-Levy solution. And using these three ingredients, we can prove that index of D, this is on X, is equal to index of D hat on D hat sub M on R times X. We can prove this proposition as follows. Assume phi is in the kernel of D and set phi plus and phi minus in this way. Then we can prove that this is D hat M. This is in the kernel of D hat M. You can prove it, you can check it easily. And using this observation, you can prove this proposition. Okay, so anyway, index of D hat M is equal to the original index of D. This is called product formula. Now, we will use the Atiyah-Patodi-Singer formula on R times X. Note that kappa hat here is equal to +1. Kappa hat here is equal to -1. So this operator, the same one here, is equal to D plus M gamma and D minus M gamma here. So D hat M interpolates D plus M gamma and D minus M gamma. This one. And we want to use Atiyah-Patodi-Singer index theorem, but kappa hat has a discontinuity. So as I said before, perturb kappa hat very slightly near this region. To get a smooth operator, and index is invariant this perturbation if the perturbation is small. And then we use the Atiyah-Patodi-Singer index theorem on this very simple manifold cylinder. And as I assume X is of even dimensional, so this cylinder is odd dimensional. So the constant term in the asymptotic expansion of the heat kernel vanishes. So the Eta invariant term remains. And then we get this formula by Atiyah-Patodi-Singer index formula. And we call it Atiyah-Patodi-Singer index formula. Now we can prove this toy model in this way as follows. As I said to you, by the product formula, we have index of D is equal to index of D hat M. And by the Atiyah-Patodi-Singer formula, we have index of D hat M can be expressed in terms of Eta invariant of D plus M gamma and D minus M gamma. This is a proof of our toy model. And we want to generalize this proof to the case of compact manifolds with boundary. Are there any questions? Would this result hold if you have a more domain walls? Yeah, if you have a separate domain walls, you can generalize this formula. Are there any questions? Now let's move on to the main part, the proof of our main theorem. Because that this is a main theorem, we want to express the Atiyah-Patodi-Singer index in terms of the Eta Invariant of domain wall fermion Dirac operator. And the proof is in some sense modeled on the original embedding proof of the Atiyah-Singer index theorem. First, embed x plus hat. This is a cylindrical manifold. X plus hat is this one. Into cylinder. This is the most tricky and interesting part of our proof. And extend the hat, the operator d hat on this cylinder and domain wall fermion Dirac operator on here to the whole cylinder and use the product formula and Atiyah-Patodi-Singer formula, and there is a new ingredient, Witten localization argument. And then we can prove this formula. Now let's move on to the detail. First, we embed x plus hat into r times x. Because that, as I said to you, x plus hat is a cylindrical and manifold, this one. And we can embed x plus hat into r times x as follows. This is our direction. And this is x direction. This is x plus, and this is x minus, and this is y. So this is x plus, and here there is y. And this is minus infinity times 0 times y. So this blue one is x plus hat. If this is a tricky embedding, so we will give a more concrete example. If assume for a moment, forget for a moment that x is even dimensional. So if x is S1, if x is S1, if x is equal to S1, this one, this is x, and this is y, and this part is called x plus, and this part is called x minus. Then x plus hat is a cylindrical and manifold, and in this case, this is x plus, and these 2 points are y, so this is x plus hat. And what is r times x? R times x is just a cylinder. This is x, and this is our direction. And here, you can find x plus. And here, you can find y. And so, you can embed x plus hat, this one, into R times X. This is what I said in this slide. Do you understand? Okay, anyway, we can embed long cylinder into a long cylindrical and manifold X plus hat into a long cylinder. Now we want to introduce a new operator d hat n on this cylinder. This is also an interesting part. We first observe that R times X minus X plus hat, this blue one, has two connected components, this one and this one. We denote R plus X minus by this one, is here. And this part is called, this circle part is called R plus X. Okay, and we want to introduce kappa hat APS. APS is Atiyah-Patodi-Singer. Atiyah-Patodi-Singer. The APS stands for Atiyah-Patodi-Singer. Are there English? Do you need to smooth? Yes. There are no corners. We assume the smooth embedding. So this is, there are no corners. So we want to introduce kappa hat APS on this cylinder. And this is a step function, which is equal to 1 here, and which is equal to -1 here. And we consider this operator as before. But we need kappa hat APS. The observation is that here, kappa hat APS is just this one. This is equal to kappa, the original kappa. Now we have a Atiyah-Patodi-Singer formula, which says, as before, index of d hat. We need to first put up something, and APS formula says index of this operator is equal to this one. This lives here, and this lives here. The proof is exactly in the same way as our toy model, so we omit the detail. Next, we observe that this is a technically most hard part, and the restriction of this d hat m operator, d hat m, to the tubular neighborhood of X plus hat. This is a tubular neighborhood. Is isomorphic, just a coordinate change of this simple operator. And this lives on R times cylinder, this tubular neighborhood. And using this observation, we have proved that there is a localization. Localization occurs. For m very, very big, we have index of d hat n is equal to this operator. This is a 1 on R times X plus hat, this operator. And the proof is very technical and too technical to state here, but the idea is very simple. As I said to you, this is a Jackie-Levy solution, and this is a domain or fermion Dirac operator on R, and this is a solution, typical solution. And as you can see that if n grows bigger and bigger, then this function concentrates at the origin. Basically, the proof is a generalization of this observation. But actual proof is very technical. And we have a product formula as before. Index of this operator is equal to index of this operator. D hat operator. D hat is an operator on x plus hat. X plus hat is this cylindrical end manifold. Now we can prove our main theorem. For m very, very big, we have a formula index, Atiyah-Patodi-Singer index of D restricted to x plus can be expressed in terms of this Eta invariant of domain wall fermion Dirac operator and the Pauli-Villars term. Now, by definition, we have index of this Atiyah-Patodi-Singer index of D restricted to x plus is equal to index of D hat on x plus hat. And next, by the product formula, we have index of D is equal to this operator. And by Witten's localization argument, for m very, very big, we have this equality. And finally, by the Atiyah-Patodi-Singer index formula, we have this equality. And combine these equalities, we can prove our main theorem. That's all. Thank you very much.